Hello and welcome to my talk on a new perspective on lambda-rings. My name is Stahlhauer and I'm a PhD student at the Max Planck Institute for Mathematics in Bonn. My supervisor is Stefan Schwede. My talk today is focused on power operations on certain algebraic structures, mainly on lambda-rings and beta-rings, what the differences are and how we can provide a unifying framework for these two situations. If you want to look into more detail on what I talk about today, you're invited to look at the preprint I have on the archive, and also with any questions just feel free to write me an email. Okay, so let's start with the talk. My motivation in studying power operations comes from algebraic topology, and in algebraic topology we study spaces using algebraic invariants, and one of the main tools we have here are cohomology theories. And maybe the most used cohomology theories are singular cohomology, K-theory, and also stable cohomology. And a slogan which is often useful when working in algebraic topology is that the more algebraic structure we can put on our invariants, the more we can detect on the spaces we study. And the first incarnation of the slogan is multiplications on cohomology. So one basic example is the cup-product in singular cohomology. And this cup-product allows us to distinguish, for example, the spaces S2, which S4, and CP2. And because those two spaces are CW complexes, where the only difference is the attaching map of the 4 cell, we see that these attaching maps have to be different. And this means that the Hopf map is not non-homotopic, and hence is a non-trivial element in the third homotopic group of the 2 sphere. And we can go even further and put even more structure on our cohomology series. And one example of this are power operations. And maybe the first example you see when starting to learn algebraic topology are Steen squares. The Steen squares are some power operations on singular cohomology with F2 coefficients, and they allow us to also conclude that the suspension of the Hopf map is not homotopic. And this then is an element in the first stable homotopic group of the spheres, and this group is Z mod 2 on exactly this generator. Another example are Adams operations on K-theory, and here one application is an easy proof that there are only 4 maps of Hopf invariant 1. Okay, where do these power operations come from? In stable homotopy theory, the common viewpoint is that cohomology series are represented by spectra. And I wrote down here in the table the representing spectra for singular cohomology, where we have an Algebraic spectrum, for K-theory, we have a K-theory spectrum, and for stable cohomology, where we have the sphere spectrum. And all of these operations, so the multiplications and the power operations, those arise from the structure of an E-infinity ring on the representing spectrum. So there's a notion of a commutative ring spectrum here, and this gives us the power operations. Okay, so that's the topological framework we want to work with. Now we can also ask ourselves, how do we organize the algebraic power operations on the cohomology series? One example, which is maybe classical, is that of Steen squares. Those assemble into the so-called Steen algebra. It's an algebra of all the Steen squares, and all relations between those are encoded in this algebra. So we want to do something similar for, let's start with K-theory, where we arise at the structure of a lambda ring. And we can do the same thing with representation theory, so there we study representation rings, and we start by introducing these two objects. So what is K-theory? We can restrict ourselves to an easy special case, so the zeros K-group of compact space. There we just study isomorphism classes of complex vector bundles over X. And these come equipped with an addition by direct sum, so we can form the group completion with respect to this addition. So we form formal differences of these vector bundles, and then this is a ring with the multiplication given by the tensor product. And in a similar fashion, we can define the representation rings. So we start with a finite group. We consider isomorphism classes of finite dimensional G representations, and then also there we take formal differences, and this is a ring with direct sum and tensor product as operations. Okay, and just so that you get a feel for this, what are easy examples of representation rings? First of all, you see that additively, the representation rings are always free on the irreducible representations. And for some small groups, you can just write down the entire ring. So if we consider the trivial group, then we just have vector spaces. So those are classified by the dimension. So the representation ring of the trivial group is just the integers. For the cyclic group with two elements, we have two irreducible representations, namely the trivial one and the one-dimensional sign representation. So those are additive generators, and the multiplicative structure is governed by the fact that the square of the sign representation is trivial. And then for a little bit more of a complicated example, we can take the symmetric group of three letters. This has three irreducible representations, namely the trivial representation, the sign representation again, one-dimensional, and the two-dimensional reduced permutation representation, which I defined here. And those are additive generators, and multiplicatively the relations are as I wrote those down here. Okay, so these are easy examples of representation rings, but additional multiplication is not everything we can put on here. We can also put on here power operations, and those are usually encoded as lambda operations. So for these we study the n's tensor power of a representation, and this has a sigma n action by permuting the factors. And we can now impose the relation that the sigma n action should act like the sign representation. So that if we permute two vectors, we should act by a -1 sign. And then we get the alternating power of the vector space. And this has a g action just by the diagonal action. Okay, and we can check that this construction for vector spaces also extends over formal differences, so we get an operation on the entire representation ring. Alternatively, we could also consider symmetric powers, so we don't enforce the relation that a twist acts with -1, but we enforce the relation that every permutation acts by the identity. So this then is a symmetric power. And this also we call beta n of v. But historically, the more important thing was the lambda operations, so those are the ones we will focus on. And of course, both of these constructions can also be done with vector bundles, so we can also give these definitions on the zeros k group of a compact space X. Okay, and just to get a feeling for these lambda operations, here are some examples. If we have a k-dimensional vector space, then the n's alternating power has dimension k over n. So on the integers, which are the representation of the trivial groups, that's exactly what the lambda operations do. On the representation ring of the cyclic group here, the sign representation is one-dimensional. So here we only can have a lambda 1. That's the same argument as in the first case. And lambda 1 is always the identity, because the first alternating power is just the representation you started with. So that's very easy. But we can also consider, for example, 1 plus the sign representation. And here we can calculate lambda 2, and that's again the sign representation. And in the representation ring of the symmetric group on three letters, there is a two-dimensional irreducible representation, and lambda 2 of this turns out to be the sign representation. And this, in fact, completely determines the lambda operations on this ring. And if you consider a bit longer what these lambda operations do, you arise at a few properties these have to satisfy. So for example, the zeros lambda operation is always trivial, and the first lambda operation is always the identity. Those two just come from the definition by alternating powers. Then you have an additivity formula, which is similar to a binomial formula. So if you take an alternating power of the sum, you get some sum of products of lambda operations. And you also have universal formulas for the lambda operation of a product and a composition of lambda operations. And these universal formulas are polynomial in lambda i's of x and y and lambda I of x, respectively. And they don't depend on x or y or of the ring we are working in. So these are really universal. And once we have these properties, we of course can define a lambda ring to be just a ring together with these operations lambda n satisfying these properties. And just from the way we build this definition, you directly see that the representation ring and the K-theory ring both are lambda rings with these operations. Okay, so this is now a nice formalism to work with power operations on these two objects, but we would maybe like to have an even nicer description. If you think back on the example of the steamroll algebra, then you saw there we had the steamroll algebra, which was like a universal thing where we have steamroll operations. And we can try to do a similar thing on lambda rings. So we want to have a universal or a free lambda ring where all these operations are encoded. And if we want to define this lambda ring, you can think that, well, lambda operations were defined using the nth tensor power of a representation or a vector space or a vector bundle. And those have sigma n actions. And these sigma n actions really played a key role in the definition of the lambda operations. So let's just study representations with sigma n actions. So we built the following ring. So we set lambda to be the direct sum of all the representation rings of these symmetric groups. And this has a ring structure where we have level-wise addition. So that's the obvious one we would take. But the product is not the obvious one, the level-wise one, but this induction product. So if we have a sigma n representation and a sigma m representation, their tensor product is a sigma n times sigma m representation by acting on both factors separately. And then we can induce it up to be a sigma n plus m representation. And this then really defines the ring structure on lambda. And it turns out that this ring is indeed polynomial on the sign representations. That's a calculation you have to do. And just an example to see how this calculation goes. For example, the regular representation of sigma n, which is the action on like a free vector space on sigma n. This is just induced up from the trivial representation. So this turns out to be lambda 1 to the n. And because we have this polynomial ring, specifying lambda operations on a ring is the same as specifying a ring map from this ring lambda into the ring of self-maps of A. So these lambda operations are equivalent to a ring map, and then the additivity, multiplicativity, and composition relation between these lambda operations also can be formalized in terms of this ring map. Okay, so this is now a nice formalism for studying lambda rings, which makes use of a universal object. And this can then be used to also generalize this formalism. So now we turn to our second example, which was stable cohomology. And the analog of representation rings in this context are the Burnside rings. And the idea is that everywhere where we had vector spaces before, we now replace those by finite sets. So we make the following definitions. So zero's cohomology group of a compact space is now formal differences of isomorphism classes of finite coverings of X. So where before we had finite vector bundles, where the fibers are vector spaces, we now have finite coverings where the fibers are finite sets. And for the Burnside ring of G, we define this to be formal differences of isomorphism classes of finite G sets, where we replaced vector spaces with the G action by finite sets with the G action. Okay, those are the definitions. And we can now try to also define power operations here. And we see that the main difference to the context before is that we don't have any additivity inside finite sets. So in vector spaces you can add elements, in finite sets you cannot. And this means that we cannot define alternative powers, because those had a minus sign in there, and minus signs don't make sense in finite sets. But we can still define symmetric powers, because there we just took the sigma n action and set it to be the trivial action. So we take this approach and we define beta n of a finite G set to be just the symmetric power of this G set. So we take the nth Cartesian power and quotient out the sigma n action. And we can do this slightly more generally. If we have a subgroup of the symmetric group on n letters, we can take the beta operations indexed by h to be taking the nth tensor power and then only quotienting out those permutations which lie in H. And this, of course, extends to the Burnside ring, and the similar operation can also be defined on cohomology. Okay, and we could now start to define a beta ring as something having these operations and satisfying certain relations. But this is a bit difficult because it's not that clear what the relations should be between these beta operations. So it's a bit easier to just directly go to the universal object point of view and define the universal beta ring. So that's what we call capital beta. That's the direct sum of Burnside rings of symmetric groups. Where before, for capital lambda, we had the direct sum of representation rings of symmetric groups. And this again has a ring structure in the same fashion as lambda had. So we have level-wise addition, and the multiplication uses this induction. Okay, and having this ring beta around, we can define a beta ring to be a ring A together with a ring homomorphism from beta into the ring of self-maps of A. And this should again satisfy addition, additivity, and compatibility with composition. But here we have to be a bit careful, because additivity is actually not a relation here, but it's extra data. And we don't have any multiplicativity relations. And I will go into detail on these 2 points a bit later. But first I want to see how cohomology and Burnside rings now really are beta rings with this definition. And for this we study the ring beta itself a bit more. So in fact, beta is generated by these finite sets, so sigma n mod h, for all choices of n and for all subgroups h of sigma n. But here, this is just an additive set of generators, not like a set of polynomial generators as we had in the case of lambda. And these additive generators just comes from the fact that the Burnside rings are generated by transitive sets, transitive G sets. Okay, and once we have these additive generators, we see that a ring map can be specified by just taking images for all the generators. So we can use the maps beta h we had defined to define the structure of a beta ring and on the Burnside ring and on cohomology. And it's then a fairly complicated check to see that this really defines the structure of a beta ring, so that these relations, additivity and composition, and also that this ring map are satisfied. Okay, so we have now a theory of beta rings, and we see that Burnside rings and cohomology are examples. But there are important differences between these beta rings and these lambda rings. And we already saw a few of these differences. So for example, on lambda we had easy generators as a polynomial ring. Those were these sign representations. But on beta, there's no such easy set of polynomial generators. In fact, beta is a polynomial ring, but for example, it's not a polynomial ring on these beta n's, those symmetric powers, whereas lambda is in fact also a polynomial ring on these beta n's, which are there as a trivial representation of sigma n. So beta, even though it's also a polynomial ring, it has a way larger set of generators, and it's not that useful to work with these generators. And then I mentioned that additivity is extra data in beta rings, whereas in lambda rings it's just a relation. So this comes from the fact that in the representation ring, if I take the product of two symmetric groups, the representation ring is just a tensor product of two representation rings. What this uses is that we can really add elements in a vector space and in a sigma n representation. And for finite set we can't do that, and because we cannot do this, the natural map we have between those two things for the Burnside rings is not an isomorphism. And so to formalize additivity in beta rings, we have to extend our beta operations over subgroups of this product of symmetric groups. And this is an additional data. Also, multiplicativity in lambda rings uses extra structure on this ring lambda, and we just don't know what the analog of the structure would be in the ring beta. So there is no useful formulation of multiplicativity in beta rings. So the consequence you should take away from this talk is that the theory of beta rings is just not as well behaved as that of lambda rings. There are a lot of complications, and it's not as nice to work with beta rings. Okay, but we talked about how all these power operations arise from common structure on the ring spectra, which are underlying or which are representing cohomology, and this was an E-infinity ring structure. However, the algebraic structures are quite different. So you might come up with the question whether there's a unifying algebraic notion of power operations, which encodes power operations coming from E-infinity structures, and which forgets both to lambda rings in the case of K-theory and to beta rings in the case of cohomology, but which is like a common notion of power operations for these two formalisms. And if you want to come up with such a definition of what an algebraic notion of power operations would be, you look at our definitions of lambda rings and of beta rings, and you see that the common theme was that we used an nth power of an object and then used the permutation action, the sigma n action, on this nth power. So maybe it's more fruitful to study this sigma n action itself and not some quotients of it. So we want to study sigma n equivariant objects for all n, and then because any finite group is a subgroup of the symmetric group, we might as well study all finite groups. And this then leads to a viewpoint of globally equivariant algebra, which I now want to talk a bit more about. So the two basic examples of like globally algebraic objects are the representation ring and the Burnside ring. So you see those are defined for all finite groups, and they satisfy certain relations. So we have restrictions for homomorphisms of groups. So if we have a G set, we can restrict the action to be a K set action. And if we have a subgroup, we can transfer or induce up the action. So that's the thing we used in defining the ring structure on lambda and on beta. And looking at these sigma n actions on powers, we can also encode power operations here. So if we have a G object, so G set or G representation, then taking the nth power, the universal thing to act on this is the Ries product, sigma n Ries G. But if you don't know what this is, you can also think about just the sigma n action, the permutation action, and the diagonal G action, and these two commute. So from a G set, taking the nth power gives us a sigma n times G set. And that's the composition I wrote down here. And just to make a definition, a collection of rings for all finite groups with these structures, so with restrictions, transfers, and power operations, and these have to satisfy some compatibility relations. This is called a global power functor. Or if you come from like a G equivariant context for a fixed group G, then this would be an analog of a Tambara functor. Okay, and how do these global power functors fit in our theory? Well, if we have a so-called globally equivariant commutative ring spectrum, then the represented cohomology for any space is a global power functor. And this can be applied to our examples because those all have equivariant theories refining those. So there's this notion of equivariant K-theory, there's equivariant cohomotopy, and there are also equivariant singular cohomology theories, so Breton cohomology, these things. So in this way, we have like a connection to the topological side, and we also can reconstruct, for example, beta operations from this global power operation on the Burnside ring. So this uses so-called deflations. So we can consider the following thing. If we have a sigma n set x and a sigma n times G set y, then we can take the balanced product. So we take the product of x and y, and we equate the two sigma n actions on x and on y. And this still has a G action coming from y. And if we use this definition, we can recover our H-index beta operation by seeing that this is the same as this balanced product of an n-fold power of x and this transitive sigma n set sigma n mod h. So we can in fact factor our beta ring structure by first using the power operations, these global power operations, and then using this deflation product. Okay, and in the same way, using these sign representations, we can also recover the alternating powers on the representation rings. And so now we come to our conclusion. So we saw that global power functors, those sit in between the topological multiplication of spectra. So if we have like a ring spectrum with some equivariant data, we get a global power functor. And between these and algebraic frameworks for power operations. So from global power operation, we can get back a beta ring or a lambda ring structure. So it's a nice intermediate step. And in fact, it turns out that global power functors have a well-behaved theory. So they have an easy additivity relation, easy multiplicativity relation, easy relation for composition of power operations. So that's all very nice. And in fact, it turns out that they are really very close to topological multiplications. So for example, on Albert-MacLane or on Moore-spectra, it turns out that the topological multiplication is essentially equivalent to having these power operations on the global power functor. And this intermediate step also allows us to understand where all these complications in the work with beta rings come from, which are not present in the work with lambda rings. And it turns out, because both can be refined to global power functors, and this is a nice theory, it turns out that all the complications for beta rings really come from this deflation step. That introducing these deflations is responsible for all the complications in beta rings. Okay, and having said all this, the thing I want to finish with is that all these observations really are an indication that global power functors should be thought of the more fundamental notion here. So that global power functors should be thought of as the object which really encode power operations. And that beta rings can be derived from those, but this step introduces a lot of complications. So maybe it's better to just work with global power functors. And if one really has to work with beta rings, maybe one can study this assignment of a beta ring to a global power functor to understand where these complications come from. And this is also a step for maybe further research, that we want to understand this passage from global power functors to beta rings more. So I have now described you how this passage works, and now we can maybe ask the question whether every beta ring refines to a global power functor. So we saw this for cohomology, we saw this for Burnside rings, but maybe there are some exotic beta rings which don't come from global power functors, and that's something one could study in the future. So with this, I want to end this talk, and thank you very much for your attention. Goodbye.